Hello everyone. So this video is about two problems from chapter 20, and we are going to start with problem 57. So here in the part A, suppose you have 4 coins, all tails up. You now rearrange them so 2 heads and 2 tails are up. What was the change in the entropy of the coins? And then they're asking something similar for 100 coins, and you need to look up things from a table for this case. And then they're asking, compare these entropy changes to ordinary thermodynamic entropy changes, such as examples 6, 7, and 8 from second law of thermodynamics. Okay, so let's start with part A. Here we have just 4 coins, all tails up. So you start with 4 tails, and then from this you go to 2 tails and 2 heads situation. Yeah. So this is problem 57. Now this one corresponds to a single microstate. So if you have 4 tails, there is just no way to arrange this. Every single one of those, every single one of your coins should be tails. Whereas if you have 2 tails and 2 heads, now there are a number of ways you can actually achieve this. You can choose just the first 2 coins to be tails, or the last 2 coins, or the first and the third one, and so on and so forth. But the bottom line is that this corresponds to a larger number of microstates. So this actually corresponds to a single microstate, one microstate, or let's call this one way, and this corresponds to 6 microstates, or 6 ways, right? And from this you can actually calculate the entropy, because the entropy is just given by Boltzmann Constant times the natural logarithm of the number of ways you can arrange a system. And this is just going to be S1 is going to be K times ln1, which is just 0, and this is going to be K times ln6, which is just some number. Okay, so you can just look up the value of Boltzmann Constant. So here you have an increase in entropy from 0 to some finite number. Okay? Now for part B, you're doing this for 100 coins. So instead of 4 tails, you start with like 100 heads, I think. Oh, sorry, you start with equal and equal, right? Is that right? Yeah, they're mixed random initially, 50 heads and 50 tails, and then you arrange them so all 100 are heads. So it's the same logic, but let's just go over this again. So you start with 100 heads. Oh, sorry, 50 heads and 50 tails, and you go into 100 heads and 0 tails. Okay? And again, there's a corresponding number of microstates for this. You can look this up from the table. This one is obviously, there's just one way to make this arrangement. There's just one microstate. This one, if you look it up from the table, given there, so this is 1 times 10 to the 29. So there are 10 to the 29 ways that you can do this. Now this might not be obvious at how you count this, but there are well-established ways to actually calculate these formulas without calculate these numbers without actually writing down every single possible way. Right? And so if this is the way, then you can calculate the entropy. So S1 is going to be K times ln 10 to the 29, which is actually 29 times K times the ln 10, and ln 10 you can look up. S2 is just 1. S2 is just 0, sorry, K ln 1, and that's just 0. Right? And this time our entropy started with a finite number and decreased down to 0. In part C, they're asking to compare this to natural entropy changes, things like that. So in a natural process that you see around you, the entropy change is going to be of order 1 joule per Kelvin. So for example, in one of the examples there, an example 20-6, you'll find that the entropy change calculated is about 10 joules per Kelvin. Right? So this is what you expect. Now what about these numbers that you find here? Well, so this is something around 10, this is something around unity, so their product is, let's say, 100. But this thing here, Boltzmann Constant, if you look it up from the cover of the book, so let me just do that. Boltzmann Constant is 10 to minus 23, 1.38 times 10 to minus 23 joules per Kelvin. So K is around 10 to minus 23 joules per Kelvin. So the thing that you find here is going to be something like 10 to minus 20 joules per Kelvin, much smaller than the ordinary entropy changes that you will find for the physical processes around you. And the reason for that is that there are a very small number of particles here just 100 particles, whereas in the processes mentioned in those examples, there's an Avogadro number of particles. And if you increase the number of particles, of course, the number of microstates also increase in an exponential way, and you take the logarithm of that, so there's this there's a suppression of those effects. But because the number of microstates actually increase exponentially, then you still get a very large difference between the entropy changes with systems with an Avogadro number of particles versus just particles of order 100 or so. All right, so let's look at question 58. So that's a little bit more complicated, but it's actually basically the same problem. So let's take a look at that. So here, consider an isolated gas-like system consisting of a box that contains 10 indistinguishable atoms, each moving at the same speed v. The number of unique ways these atoms can be arranged so that NL atoms that are within left. So first of all, these are distinguishable, right? This is normally not the case, but in classical mechanics, we presume that you can actually follow these atoms, so you can actually tell which atom is which, even though quantum mechanically this is not possible. So yeah. So this NL, so they have this chamber on the two sides, and this NL is the number of atoms on the left, and R is the number of atoms on the right side of the chamber. So here in the state A, you have all 10 of them on the left, none on the right. In state B, you have 5 of them on the left and 5 on the right. Now, because the atoms are distinguishable, saying that 10 on the left and 0 on the right doesn't correspond to any microstate. It's just there's one microstate, but this one, state B, 5 on the left and 5 on the right, can actually be done in a number of ways. Right? Let's say that you can take this atom and replace it with this atom, and that is, even though it's the same macrostate, NL equals 5 and NR equals 5, is in fact a different microstate. So this one is going to have a number of microstates, whereas this one is going to have just one microstate. Right? So this is the same situation. So being on the left or on the right for each atom is like for a coin to have heads or tails. Right? So if you arrange it such that they're all on the left, then they all have heads, let's say, whereas if some are on the left, some are on the right, some are heads, some are tails. So more microstates correspond to this mixed situation. Now imagine the following two possible macrostates. State A, where, okay, this is state A, this is state B, and they're asking us, assume that the system is initially state A and at a later time is found to be state B, determine the system's change in entropy. So what will be the arrangement here? So they actually give you the number of ways here. This is n factorial, n is the total number of atoms, divided by nl factorial, factorial of the number of atoms on the left, divided by nr factorial, factorial of the number of atoms on the right. Okay, so we can calculate this for state A. So the number of ways for state A is just this formula, nl factorial and r factorial. This is just 10 factorial divided by 10 factorial, 0 factorial. 0 factorial by definition is 1, so this is just going to be 1. Okay? Whereas for state B, you still have the same formula being applied. Okay? And this is going to be n factorial. We still have 10 atoms. Now 5 of them are on the left, so it's 5 factorial, and 5 are on the right, so this is 5 factorial. We can just calculate these numbers, and you're going to find that this is actually larger than 5. So let's just do this. So this is going to be 10 times 9 times 8 times 7 times 6 by 5 times 4 times 3 times 2, 1. So these cancel. This is going to give 2. This cancel. This will give 2. This will give 3. And this will, let's say, cancel. So this will give 4 actually. No, it's 2. Okay, so this is 6 and 6. 6 times 6 is 36, so this is 36 times 7. I don't know what this is, but it's some number. And then by knowing this, you can calculate the entropy of the two states, right? So SA is going to be K ln WA, and SB is going to be K times ln WB. This is 1, so this is going to be 0. This is going to be some finite number. So it's really very similar to what we have done for the heads and tails. Oh, I didn't actually switch to my my whiteboard view. So let me just go over this again very quickly. So this is the number of ways for the atoms being in state A, all of them in just one chamber, in the left chamber. So this n factorial is n is just total number of atoms, so this is 10. All of them are in the left state, so this is 10 as well. 10 factorial divided by 10 factorial is 0 factorial. 0 factorial by definition is 1, so this is 1. Right? Whereas for state B, and L and R are both 5, so you just carry out this calculation and you find that this is actually something larger than 1. Right? And you can calculate the entropies of the two states. So the entropy corresponding to state A, where everything is on the left, actually is going to be 0. This is WA is 1, so ln 1 is 0, and this is going to be something larger than 0. Still something very small because we are dealing with a very small number of particles, but this is something larger than that. So this could happen spontaneously, whereas starting from state A to state B cannot happen spontaneously. So I think this is what they're asking in the other part. Can this process occur naturally? Yes. The other process, no, it can't occur naturally. So yeah, the calculation here is a little bit more complicated, but they are giving you the hard part, this n factorial divided by n left factorial and right factorial. So if you're allowed to use this rather than trying this yourself, then this problem is very similar to actually the previous problem, 57. Okay, I think that's all I want to say for this.